And, a lot of what we did last week and a lot of what we're going to do today is really just an extension, another layer added on what you did last year in Math 20-1. Last year in 20-1, you learned these three trigonometric ratios: cos of theta equals x over r, sine of theta equals y over r, and tangent of a rotation angle is equal to y over x. That was a new concept last year when you kind of abandoned the idea of opposite, adjacent, and hypotenuse in favor of y, x, and r. And in a right angle triangle, we could always say hypotenuse squared equals opposite squared plus adjacent squared. Well, here what we can say is for any rotation angle, x squared plus y squared is equal to r squared. So the relationship between x, y, and r is a Pythagorean relationship. It's just that as soon as you rotate past quadrant 1 and into quadrant 2 and quadrant 3 and quadrant 4, the concept of a Pythagorean triangle, it doesn't exist anymore because it's just a rotation angle. And then what was new last week on Friday was secant of theta is the reciprocal of cosine of theta. And on your formula sheet, you're given that information, but you're not given the definition of any of these in terms of x, y, and r. But you are told on your formula sheet that secant of theta is the reciprocal of cosine of theta. So if cosine of theta is x over r and secant is the reciprocal of cosine, then secant of a rotation angle is r over x. Cosecant of theta is defined as the reciprocal of sine, and the reciprocal of y over r, which is sine of theta, would be r over y. And then cotangent and tangent are reciprocals of each other, so if tangent of theta is y over x, then cotangent of theta would be, well, the reciprocal of y over x, x over y. So let's take some time today and go over these questions. Many of these questions didn't require, but would be helpful if you knew features of the unit circle. You don't have to. You can kind of, as I say, weasel and maneuver your way around the unit circle if you have to, but if you know the unit circle, it's much easier. So an example of putting this whole set of ideas together with the unit circle would be if I asked you for the cotangent of 7 pi over 6. If I said to you, what is the exact value of the cotangent of 7 pi over 6, the first thing you would need to do would be to locate where 7 pi over 6 is on the unit circle. And by the way, it's an expectation that you can locate 7 pi over 6, period, whether it's on the unit circle or not. Pi over 6 is a 30-degree chunk. So when you start looking at 7 pi over 6 in terms of my arm motion, here's 1, 2, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6 is in quadrant 3 with a reference angle of pi over 6 or 30 degrees. So this is 7 pi over 6. Now if you want to start talking about the unit circle, and I'll get back to the whole cotangent idea in a second, the unit circle in quadrant 3 will intersect that terminal arm in some particular place. We call this point P. Remember that this is -1. This is -1 because I'm thinking of the unit circle. This is one way to do it. I'll show you an alternate way to do it in a second. And knowing the coordinates of that point is the key to determining cotangent of that angle, tangent of that angle, sine of that angle, cosine of that angle, cosecant of that angle, and secant of that angle. And I've taught you some kind of tips and tricks here. First of all, that angle or that position is not the halfway mark between the axes. So it's not the root 2 over 2, root 2 over 2. This will have an ordered pair where one of the numbers will be a half and one of the numbers will be root 3 over 2. And you have to decide which is which. And since this number here is -1, you can see visually that this distance appears to be 1/2 of that distance. We can call it -1/2, but you can see the y coordinate is -1/2. So we're going to put the half in here. We're going to put the root 3 over 2 in for x. We're going to say to ourselves, since it's in quadrant 3, both of these are negative. And now we can answer the question. The question was, what is cotangent of 7 pi over 6? So we run through this procedure in our head. We say cotangent is the reciprocal of tangent. And I know, so this is what's going on in my head. I know that tangent of a rotation angle is y over x. So if cotangent is the reciprocal, then cotangent of theta is x over y. Now, there may very well be some of you that don't have to go through that question of what tangent is to know cotangent is x over y. Some of you might just know cotangent of a rotation angle is x over y. But anyway, now that we've figured out it's x over y, I can look at the x coordinate, which is negative root 3 over 2. And I'm going to divide that by the y coordinate, which is negative 1 over 2. Kind of painted myself into a corner here. I need just a little more room. This is what you call a complex fraction, which we frown upon in math. It's not that there's something wrong with it. It's hard to understand. So I'm going to simplify this fraction by multiplying the top and the bottom of this expression by 2. And the goal or the strategy is that these will cancel, and I'm left with negative root 3 over negative 1. The negatives cancel, and you don't have to write over 1. So this is one application of the whole XYR thing. Could you have cheated? Could you have figured out what that is without relying on the unit circle? Well, certainly. And I won't say that this method of cheating is one where you have zero understanding of trigonometry. You have to understand a lot of what's going on here to cheat on your calculator. The first thing you need to understand is that you're going to have to be in radians, because 7 pi over 6 is an angle in radians. Although you could convert it in your head to 210 degrees and just use degrees. But I'm going to go 7 pi over 6. The other thing you need to know is what cotangent means. So I'm cheating here by looking just at the question, the thing that's highlighted. What does cotangent of 7 pi over 6 mean? It means 1 divided by tangent of 7 pi over 6. And I get this number, okay? And I cross my fingers as a student who maybe is not really that comfortable with the unit circle, and I go, I'm going to convert that to a fraction because I need an exact value. So I cross my fingers and I go math, enter, enter. And the fact that my calculator is unable to convert this to a fraction tells me it's not a rational number. Now, the only irrational numbers you're going to encounter so far in this unit, in this type of question, will be square roots of things. And that means that this number must be equal to the square root of something. So look at what I've written here. I've written 1.73, I'm not going to write all the decimals, equals the square root of some number. Well, how can I find that? I can square both sides. And that will give me the number that's under the square root. So if I square that, what do I get? I get 3. Oh, so that's root 3. Now, you may think, well, that's a lot easier than what we did, but it's going to let you down sooner or later. And there's lots of different variations that you can have here. It's not always going to be 3. It could be You have this number. Could be you have this number. Now, how many of you recognize that's root 3 over 2? I mean, if you do, that's great. If you don't, you're going to have to square it to find out what it's the square root of. And it's the square root of 3/4. So how would you write the root of 3/4 as a simplified radical? You'd write root 3 over 2 because the square root of 4 is 2. Okay. The other types of questions that you were dealing with would be these types of questions where you know x and y and you need to find out all the trigonometric ratios. The thing that you have to be cautious of here, and I will give you a specific illustration of this, is something like number 4, where you're given some information there. Cotangent is x over y. We've already established that. So cotangent of theta is x over y, and it's equal to negative 3/4, and you have to decide, where does that negative go? Does it belong with the y or does it belong with the x? And you have to look at the fact that cosecant, which is, so now there's more thought going on. Cosecant is the reciprocal of sine. Sine is y over r, so cosecant of theta is r over y. The only way that can be negative is if the y is negative. So the negative belongs with the 4. Then you would use x squared plus y squared equals r squared, which I know everybody can use to find r is 5. And then if you want to find the value of sine, it will be the y coordinate over r. So I want to spend quite a few minutes on this because I know that this is, there's a lot here. Honestly, I don't believe that this is difficult math. There's just so many things. So now I'm going to ask for questions. Can you take a look at your textbook first? Does anybody have any questions from 1, 2, 8, 12, anything from this section that you would like me to go over? Does anybody have any questions you would like me to go over from the additional problems that are in the handout? Go ahead, Marcel. 3, certainly. I'm going to show you another kind of method that you could use to cheat here in a second, but we're going to do this the quote proper way, the way that Math 30-1 is designed for you to follow. So we have secant of some angle. The fact that it's not theta but just called p shouldn't be a problem. It's just a letter. It's a variable. Is equal to 2. And there's so many different ways you could think of this, and maybe that's what else is making this confusing at times. I would probably here express this as a fraction and then go through this procedure in my head of saying, what is secant the reciprocal of? And it's the reciprocal of cosine. So this is the reciprocal of cosine of p. And cosine of p is defined as x over r, which means that secant of p is r over x. Which means that this is r and this is x. Those are not exponents, obviously. I'm just slapping some labels on there. If you want to find the value of sine, sine of P will be defined as y over r, because sine of a rotation angle is always y over r. So we do know what x is. X is equal to 1. We do know what r is equal to. R is equal to 2. But we don't know what y is equal to. And the reason we need to find out what y is equal to is because we have to put y divided by r to get the answer to the question. Oh, thank you very much, Kelly. Pi r squared, yeah.
But I didn't have the right size pan, so you got to round it by.
Oh, thank you very much. Take care. So we need to find y, and now what we're going to do is use the Pythagorean theorem. So I can write with the Pythagorean theorem x squared plus y squared equals r squared. X is 1. We don't need the brackets, but you know how I am about that. Just put a set of brackets just to be sure. Plus y squared, which we don't know, equals 2 squared. So when I simplify that, I get 1 plus y squared equals 4. And I subtract 1 from both sides to get y squared equals 3. And then, you know, I'm just zeroed in on math right now. I'm not looking at the context. I'm looking at that equation. And when I solve that equation, I have to say plus or minus the square root of 3. So it is a mathematical possibility that y equals the square root of 3 or negative 1 times the square root of 3. And I have to go on a little journey here to find out. Oh, it's in quadrant 1. To find out something about where that terminal arm lies. And if it's in quadrant 1, in the first quadrant, x is greater than 0, y is greater than 0. So that little peak up there tells me that it's not negative root 3, it's positive root 3. And then I can write my answer, y over r, so the sine of the rotation angle is root 3 over 2, which would be d. Is that okay? You bet. Now there is a, you know, because a lot of the time the questions we're doing are multiple choice or numerical response, there's another way you could do this, a very simple way to do it. And it's kind of connected to what we're going to be doing today. I'm in degrees just so we can, you know what? Let's go in radians because it's not going to matter. And I want to do it in radians for a reason that is known only to me. Don't worry about why. If secant of angle P is 2, that means that cosine of angle P is 1 over 2. And this thing that I've circled is equivalent, everybody, to all of this thinking that I did on the right-hand side about r and x being reciprocated relative to each other from secant to cosine. In other words, since secant is the reciprocal of cosine, I'm just going to say cosine is the reciprocal of secant and flip it over. But what I can do now, and this is just a very quick way to get the answer to the question, equal to 1 over 2, then inverse cos of 1 over 2 gives me angle P. So this is the angle. Are you with me? What do I want to find? I want to find the sine of P. So why don't I just take the sine of that angle? I know what the angle is. Let's figure out what the sine of the angle is. And it's this number, which is root 3 over 2. So there's other things you can do here. Any other questions before we get started today? Go ahead. 5? Certainly. So we're given cosine, and really, I know I was guilty of going too fast on Friday, and I apologize for that, but at some point, everybody here needs to graduate to the point where you say cosine of an angle is 4/5. Oh, x is 4, r is 5. Right? Like some of this should be becoming more natural to you, more obvious, more known. So since cosine of theta is x over r, that means we can say x is 4, and r is 5. And we want the value of cotan, and I'm not going to write down my thinking here, but cotangent of theta is the reciprocal of tangent of theta. Tangent of theta is y divided by x, so I have to flip that y over x over, and this is the answer to the question. Cotangent of theta will be x over y. We just need to load in whatever x is there and load in whatever y is there, and we will have our answer. Does that make sense, Leslie? Okay. So, again, knowing 2 of the 3 of x, y, and r allows you to find the third. So if I know x and r, I can find y. And that's what I'm going to do over here. I'm going to write x squared, which is 4, quantity squared, plus y squared, which we don't know, equals 5, quantity squared. 4 squared is 16. So I have 16 plus y squared equals 5 squared is 25. And I end up with y squared equals, well, whatever 25 minus 16 is, which is 9. And the square root of 9 is 3, but we want to be very careful here because the square root of 9, once you get to grade 11, the square root of 9 is not 3, it's plus or minus 3, right? We have to say plus or minus root 9, which is plus or minus 3. So we have three choices. We have 2 choices here. Y can be positive 3 or negative 3. And now we need to, look through a magnifying glass at this question and the information to find out where the terminal arm is. If the terminal arm is in either quadrant 1 or quadrant 2 up here, then y will be positive, and if the terminal arm is below the x-axis in 3 or 4, y will be negative. So what does this mean? Well, 3 pi over 2 is less than theta, which is less than 2 pi. Here's 3 pi over 2. Here's 2 pi. And we know that theta is between those numbers, so theta has to be in this quadrant. And that means, I don't know if it was theta or a, it doesn't matter, but that means that y is negative. So now that we know y is negative 3, we can kick this one out. Y is negative 3. The value of cotangent is going to be x, which is 4. So I'm just looking at this, Leslie, here. It's x, which is 4, over y, which is negative 3. So it's negative 4/3. And again, that negative doesn't have to be put with the y. It can be put wherever. Is that okay? Okay. All right, let's move on. And today what we're going to do is an extension again. Just a very minor extension from Math 20. Okay? I've called this Part 2 of Section 4.3 and Part 1 of Section 4.4. And I've mentioned this before. The second part of 4.3 is really exactly the same thing that's going on in the first part of 4.4. There's not 2 different topics here. What we're doing is we're finding angles or solving equations. In 4.3, they call it finding angles. In 4.4, they call it solving equations. But when you're solving a trigonometric equation, that's exactly what you're doing. You're finding an angle. So we're going to be solving trigonometric equations. We're going to spend a couple of days on this. One day on this lesson, and then tomorrow we'll look at more complicated ones. And the only difference between these 2 objectives is the domain, whether it's a specified domain, like what are the solutions to the equation between 0 and 2 pi, or whether it's what are all of the solutions to the equation over any real number. So we're going to be looking at determining the rotation angle if you know the value of the trigonometric ratio. This is kind of like that where we had, I think it was secant of p equals 2. Remember we did that question? I found the angle on my calculator. We didn't have to do it that way, but I wanted to show it to you. So consider this statement, sine of theta equals 1 over 2. show that 30 degrees is a rotation angle that makes it true. Well, how do we do that? Well, could do it this way. Could put our calculator into degree mode, and we could take the sine of 30 degrees. It's equal to 0.5, so 30 degrees is an angle that makes that equation true. We could do it that way. Show that 150 degrees is also a rotation angle. So we could go sine of 150 degrees, and you can see that it's a rotation angle that makes that equation true. There's nothing we really need to write here. We've just convinced ourselves that there's at least two numbers for an angle that will make that equation true. What we've really done is come up with what we call solutions to this equation. Okay. We didn't have to do it that way. What we could have done is we could have looked on the unit circle, and I've just taken the time to make a nice diagram here. If this is the unit circle, then this is 1, and this is 1, and you should be able to come up with the coordinates of that point. So we could have shown that sine of 30 is 1/2, not by going to a calculator, but by drawing this and reasoning out that if this is 1, this must be 1/2, which means the y coordinate here is 1/2. And quite frankly, I don't care what the x coordinate is, because the sine of the angle is the y coordinate on the unit circle. So sine is 1/2. By the way, the x coordinate here, which we really don't care about, is root 3/2. Notice, by the way, that the reason 30 degrees has a sine of 1/2 and 150 degrees has a sine of 1/2 is because these two angles, or terminal arms rather, share the same reference angle. They're both 30 degrees above the x-axis, so they're both going to have the same y coordinate. And I'm thinking of a y coordinate because sine is y. So you could do it this way and say sine of theta equals 1/2 when theta is 30 degrees. When theta is 150 degrees, you could say that sine of theta is also 1/2. So no matter how you cut it, 30 degrees is a rotation angle that makes that statement true, and so is 150. And I just want you to make a note that that means 30 degrees and 150 degrees are solutions to sine of theta equals 1/2. They're solutions to the equation. Now, I haven't shown you how we could find those solutions because I gave them to you. I didn't give you the equation and say, what are the solutions? I said, check these two out and see that they work. Just to let you know, the word solutions, or solution I'll go with, in mathematics is the same as root. So if you're ever asked to find the roots of an equation, you're asked to solve that equation. Do all coterminal angles to 30 degrees make that equation true? Well, let's just stop for a second, go back to my diagram. I'm going to clear out some of the clutter here. If 30 degrees is a location, or rather an angle that makes that equation true, it happens because the y coordinate at that point on the unit circle is 1/2. What is a coterminal angle? Well, 30 degrees, I'm going to list some coterminal angles to 30 degrees. If I add 360 to that, I get 390 degrees, I believe. That's right, isn't it? 30 plus 360 is 390. So where would 390 degrees be? Well, I would start at 0 and I would go all the way around to 360, and I have 30 more to go. I end up in the same place. So the same y coordinate exists there. If I were to look instead at negative 330 degrees, that would mean I would start here at 0 and I would go negative 90, negative 180, negative 270. I need another 60. kablam, I end up in that same place. If I end up in the same place, which I will, because that's what coterminal means, I'm going to have the same y coordinate. Different paths, same destination. So the bottom line is, if you have an angle that's coterminal with an angle that's a solution to an equation, then that coterminal angle is also a solution. And I can go through the same argument with 150. The answer is yes to both of these questions. And I don't think we need to write it down, but there's a reason. The reason is the sine of the angle has nothing to do with the angle directly. It has to do with the final place the terminal arm lands. And in all of these coterminal angles to either 30 or 150, the y coordinate of the landing point is 1/2, so sine of theta is 1/2. I'm going to pause there. Any questions with that warm-up so far?
Not a question, but I have to go to the
That's fine. Okay. I'm recording this so you can watch the rest later. Thanks for coming in for the first part. So now, what are the general statements that describe all of the solutions? So we have sine of theta equals 1/2. So how can we write that 30 degrees makes it true and all of the coterminal angles make it true? Well, we can write 30 degrees plus n times 360 degrees, where n is an integer. Now there's something that I feel I need to address, because when we first learned about coterminal angles, I said that, hear me out and think carefully about this, I said that this was not allowed because an integer includes 0. Do you remember me saying that? And if you put 0 in for n, one of these angles will be 30 degrees. And I said 30 degrees is not coterminal with 30 degrees. But that's not what this is. This has to list all of the angles that make this equation true. And 30 degrees makes this equation true, so we have to include it. Okay. There's another way to do it with whole numbers that I will show you in a second, but I would prefer this. We can also write theta equals 150 degrees plus multiples of 360 degrees, where n is an integer. So n is an integer for both of these. If you put n as a whole number, then you need to put plus or minus. And you might see that from time to time. Now, are there any questions with the warm-up? All right, so let's get to the examples. Oh, one more thing in the warm-up. On this grid, we're going to write positive or negative in each blank. So this is something that you did in Math 20. In quadrant 1, you can see the x and y axes running right down the center and across the center of all of this. Sine of theta, cos of theta, and tan of theta are all positive in this quadrant for the simple reason that in quadrant 1, x and y are both positive. And by the way, r is always positive. I'll repeat that. R is always positive. Doesn't matter which quadrant it's in. When we start to look at quadrant 2, in quadrant 2, y is still positive, so sine, which is y over r, is going to be positive. I can do this piecemeal, and I think this is a good idea. In the bottom 2 quadrants, y is negative, which means that sine of a rotation angle that terminates in either quadrant 3 or 4 will be negative. To the left of the origin, in other words, in these 2 quadrants, x is negative. So when we look to the left of the origin, x is negative, and that means that cosine will be negative in both of these quadrants. Whereas in quadrant 4, x is positive, so cosine is positive. By the way, this is not something you're trying to memorize. This is just getting your intellectual juices flowing in your head so that you can figure out which quadrants these things are positive and negative in. Tangent's a little more tricky. Tangent will be positive in quadrant 3 because in quadrant 3, both x and y are negative, and tangent is y over x. Whereas in quadrant 2 and in quadrant 4, one of x and y are positive and the other is negative. So positive over negative or negative over positive will give you a negative. So the goal here, everybody, is that if I told you cosine is negative, you know immediately it's these two quadrants, 2 and 3. If I told you that tangent is positive, it's quadrant 1 and 3. You need to be able to kind of grab that information relatively quickly. So now let's get to the example. Solve the following trigonometric equations. What makes this different is this is radians. You did this last year. So the first thing we're going to do, everybody, is find a reference angle. And the reference angle is going to be, well, let me say this first. Whenever you use a calculator to find an angle, you're not finding the rotation angle, you're finding the reference angle. Okay? And the reference angle is found by taking it's called the inverse trig ratio. This is not an exponent. That's not what this means. It just means it's the opposite operation to cosine of whatever the trigonometric ratio is equal to. Now, we want an answer in radians. You can see that the domain is expressed in terms of radians. So we need to do this in radian mode. And this is going to show us something which automatically makes us uncomfortable. That the reference angle is this many radians. Oh, I'm in degrees still. So I want to be in radians. Right? That would not make you uncomfortable because you know what 58 degrees looks like. So what makes us uncomfortable is we get an angle that is an unfamiliar kind of thing to us. 1.02 radians. But we know, everybody, since it's a reference angle, it has to be less than 90 degrees, right? And we don't really care how big it is. That's not the point of this question. So the reference angle is 1.02 rads. And that's your first step. Okay? Remember, that's not the rotation angle. That is not theta. We're trying to find theta, and that is not it, necessarily. Okay? The second step is to identify the quadrants that the angle is in. What are the two quadrants where cosine of theta is positive? So why am I saying where is cosine positive? Because look at the equation. The equation says cosine of theta is this positive number. So it's positive. Cosine is positive. Which two quadrants is cosine positive? Well, it's positive wherever x is positive, so that's quadrant 1 and 4 over here. And we draw each of these situations. We draw that reference angle of 1.02 rads in quadrant 1, and we draw that reference angle of 1.02 rads in quadrant 4. So this is the one in quadrant 1, this is the one in quadrant 4. It's been a long time for some of you since you've taken Math 20, but I want you to notice that those reference angles do not have arrows on the arcs. It's just an angle. Theta is a rotation angle to that point from 0. This is theta. This is theta. This is what you want to find. So you look at the first diagram, and we can say theta equals 1.02 rads. If it's in quadrant 1, whatever the reference angle is the rotation angle. We look at the second one, and this theta will be a full revolution minus the 1.02 rads. If we were working in degrees, you'd just say, well, it's 360 minus the reference angle. But we're working in radians, and a full revolution is 2 pi. So we can figure out what that is on the calculator. 2 pi minus the reference angle gives us about 5.26 rads. So these are both radians. These are the only two answers or rotation angles between 0 and 2 pi that if you took the cosine of them, you would get 0.524. To illustrate that, if I take the cosine of this, I get 0.524. I mean, you can't expect to get 0.524 if you take the cosine of our rounded answer. That's not going to give you exactly 0.524. Pretty far off, actually. But we're asked to round, I believe, to the nearest hundredth. Any questions with the first example, A? All right, so 3 steps. Find the reference angle. Identify the quadrants where it's true. Sketch and find the angles. Ian?
Do we have to use, or we can use decimals, but do we ever have to use?
You can use what?
We can use decimal radians,
Yeah.
but can we use exact value
Well,
radians?
if you can, yeah. Well, we'll get to that.
Oh, sorry.
Yeah, no, don't apologize. We will get to that. Yeah. So let's try this one. So the very first problem we encounter here is you don't have a cosecant key where you can go inverse cosecant. So we're going to rewrite this. Remember that cosecant and sine are reciprocals. So I'm going to take the reciprocal of that number. And I can change this to sine of theta equals 1 over negative 1.6588. And you know what, everybody? I don't care what that number is. I don't want to, I guess we could calculate it, but I don't care. Okay? So now what we have is a situation where I can find the reference angle, but when you find the reference angle, you never, ever use a negative. Even though it's a negative trigonometric ratio, we don't go inverse sine of that negative. We drop the negative. Briefly, if you include the negative, then I have to teach you what to do for sine that's different than what to do for cosine, and that's different from what to do if it's tangent. We would have 3 different sets of rules here. So I'm going to find the reference angle. Oh, look at the reference, no pun intended. Look at this, it's in degrees. Okay, we're in more familiar territory with this one. I'm going to put my calculator in degrees and find the reference angle. Inverse sine of 1 divided by 1.6588. Again, no negative. Don't put the negative in there. So the reference angle is 37.1 degrees. sorry, 37.1 degrees. Which two quadrants? So now we look at either cosecant being this number or sine being this number and say to ourselves that both of these have a y in them. Sine is y over r, cosecant is r over y. If this thing is negative, the trigonometric ratio is negative, in which two quadrants will that happen? Well, where is y negative? 3 and 4. So this is going to be in 3 and 4, in quadrant 3 and in quadrant 4. And we sketch each one and find the rotation angle. Remember, this angle that you're looking at, 37.1 degrees, is not theta. It's theta reference. So quadrant 3, we have a reference angle of 37.1 degrees. I'm just going to put 37 because I didn't leave myself enough room. In quadrant 4, we have a reference angle of 37 degrees. The rotation angle is indicated by this in quadrant 3 and this in quadrant 4. In the case of quadrant 3, I'm going to have to take 180 degrees and add that 37, which gives me 217.1 degrees. Is my addition correct? Okay. In quadrant 4, I'm going to have to take 360 and subtract 37 and get 322.9 degrees. So those are the two angles. Again, and I don't believe I'm going too fast today, but I am going to start picking up the pace a bit here. You find the reference angle, you identify the quadrants, you build pictures that give you theta. This one says exact values. And Ian had asked, are we ever going to be expected to do exact values? Well, yes. The first thing we're going to do here is prep this equation so I can find a reference angle. Okay? So I've just moved that root 3 over. And I don't want anybody to calculate anything just yet. But theta reference will be equal to the inverse tan of root 3, no negative. Now, if I give you an angle in radians in decimal form, nobody recognizes the angle. You don't recognize it. So even though this says radians, we're going to calculate the reference angle in our calculator in degrees because it's supposed to be an exact value. Let me show you what I mean. If I am actually in radians and I go inverse tan of the square root of 3, I don't know what that is. I don't know what 1.04 radians is. Well, I do, but you may not. So I'm going to instead, I'm going to repeat the calculation, but I'm going to do it in degree mode, and it's 60 degrees. Oh, okay, so that means that the reference angle is pi over 3 rads, because 60 degrees is pi over 3. That's a basic, that's what we would call, as teachers, a basic math fact. That's like saying, what is 2 plus 3? You shouldn't need to get a bunch of smarties to figure out that it's 5. It's been 5 ever since you've learned that, and it will continue to be 5 forever. 60 degrees is pi over 3. Which two quadrants? Well, even though we took the inverse tan of positive, tangent of theta was a negative number. So now you have to figure out for me in which two quadrants theta could be if the tangent is negative. And tangent is y over x. Isaiah, do you know? It is 2 and 4. Because in quadrant 2, x is negative but y is positive, and in quadrant 4, x is positive but y is negative. Did you run through that in your head, or you just remembered? In your head, yeah. So it's in quadrant 2, and it's in quadrant 4. All right, so let's sketch that. In quadrant 2, see, this is the nice thing. Even though it's pi over 3, I know pi over 3 is 60 degrees, right? And in quadrant 4, pi over 3. So what is the rotation angle? Well, this is 2 pi over 3. There's 1 pi over 3, 2 pi over 3. What about this one? This is 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. This would be 5 pi over 3. And we're done. I really believe this is the easiest, best way for Math 30 students to do this. Could you do this all in degrees and then convert your degrees to radians? Yeah, but you should be able to count off pi over 3s. So the two answers in red are the answers to this equation. Any questions with C? All right. Well, we have to rearrange for sine theta first. So I'm going to write 2 sine theta equals root 3. So sine of theta equals root 3 over 2. Now, I have a question for you. How many of you know where theta is then? I'm not just talking about which quadrants. How many of you know the exact positions on the unit circle where sine is root 3 over 2? There are those two 60-degree angles at the top. I've decided this year to try something different. Rather than saying, well, I'll do both, but you should almost know that these are the two positions based on your work with the unit circle. But you don't have to do that. Everybody find the reference angle for me, please. All you're doing is taking the inverse sine of root 3 over 2. And by the way, if we want exact values, you're going to be in degrees no matter what, because you want to see the angle. And I believe you're going to get 60 degrees. Am I right? Okay, so the reference angle is 60 degrees in which two quadrants? Well, sine of theta is positive. Sine of theta is related directly to y, whereas y positive in quadrant 1 and quadrant 2, which is what I drew to begin with. So those of you with good knowledge of the unit circle can get these answers really easily. You can just say it's pi over 3 and 2 pi over 3, or 60 degrees and 120 degrees. But we sketch it, 60 degrees in quadrant 1. That's maybe a little steep for 60, but you get my drift. 60 degrees in quadrant 2. What is the rotation angle? Theta is 60 degrees here, and theta is 120 degrees here. We still good? I'm omitting E. It's not that you shouldn't learn how to do this. You probably could figure it out. But I made a decision this semester to take some of those questions that are very rare that they would appear on the diploma exam and not include them. And you have to trust me on that. I think going through a question like this where you have this wacky domain from negative 3 pi over 2 to 2 pi right now is more trouble than it's worth in this class. It's going to cause confusion, and I'd rather not cause any confusion, or I'd rather minimize the confusion. Let's take a look at this last one, and I'm going to omit that one as well because of the weird domain. By the way, the first step of this would be to write 5 secant theta equals negative 5, to write secant of theta equals negative 9/5, and then to write cosine of theta equals negative 5/9, and find the reference angle and then locate the quadrants and proceed. It's that goofy domain that I don't want to get into, not today. Okay, so now let's talk about general solutions. Don't worry about writing any of this down that I have on the board right now. It says the general solution is a statement that includes all angles. I'm going to go to D. I believe what D was, the equation for D was 2 sine theta minus root 3 equals 0. Am I right? Is my memory right there? Okay. We saw that from 0 to 360 degrees, 60 degrees and 120 degrees were both solutions. What's the general solution? Well, the general solution would be theta equals 60 degrees plus multiples of 360 degrees. Because the general solution has to include 60 and 420 and 780, all of these coterminal angles. So all we're doing when we find a general solution is adding multiples of a full revolution. Everybody, if you're ever asked to find a general solution, find the solution in one revolution and write that down, and then add multiples of a full revolution. I'm going to pause there because I see a couple of furrowed brows. Does anybody have any questions about the answer to D here? What this question is saying is go back to example 1D and write the general solution. So what I've done is I've written the solution for 0 to 360 and then added multiples of 360. You might be confused because maybe, I don't know, the last time we talked about this, I put n times 360. It doesn't matter. Maddie, are you okay with that? Okay. Ian?
In the general solution, do you have to include n is an integer?
Yes, you should. You should put for both of these, or you should put somewhere here that n is an element of the integers. You know, and if it's a written response, Ian, and you don't put that, that's going to hurt you a little bit. That's an incomplete explanation. Both of these were also in degrees. So a general solution where n is an element of the integers would be simply adding 360 degrees times n to either of those. Whereas A and C were answers in radians, so you're going to add multiples of a full revolution, but a full revolution in radians is 2 pi. I just want to check something. Did you guys even have E and F in your handout? You did, eh? Okay. And then same thing here, you're going to go plus 2 pi n. Where n is an element of the integer number set. And that, again, the integer number set are all of the positive and negative natural numbers, so that includes full revolutions in a positive and negative direction. The integers also include 0, which would mean it would also include these specific solutions from 0 to 2 pi that we got. So that's it for today. I've got up here, and I'll just leave this up here. You can take a picture with your phone. You can write it down if you want. You can look at it in the video later. What do? You find a reference angle. You use all of your mathematical prowess to determine the reference angle. You've got to have that. You identify the quadrants. That quadrant should be pluralized. You identify the quadrants in which the reference angle is located, and you sketch the results. And then you use your sketches to determine the rotation angles. Again, when you use your calculator to get an angle, that's not theta. That's theta reference. You still have a bit of legwork to do that. So on page 211, number 2, 3, 4, and 5, notice that with number 3, actually, you know what? With number 3, just do A and B. And then 4 and 5, you know what I would say to you is if you can do 4 and 5, then you're a master at this stuff. I'm going to asterisk these and say we're going to have to learn how to do these sooner or later. None of the examples included these weird domains, but I think at the beginning of tomorrow's class I'll go over 1 or 2 of those. Okay? So that's it. I'll leave this up here so you can refer to the directions. Give me a minute or two to get my attendance out of the way. You got about 15 minutes to work on this to get a good start and get it solidified in your head, and then I'll come around and I'll help you out once my attendance is done.